Okay, before I start my talk, how many of you have written a ZK circuit? Okay, great. And how many of you have written Solidity? Great, great. Let's start the talk. Today I'm going to show you NEBRA UPA. The way we view it is that we think this is a ZK broadband that unlocks scaling, privacy, and interoperability. So this is the talk outline. So first I will tell you what is UPA, which is a universal proof aggregator. First I will motivate a little bit why we need this and what is UPA. And it's becoming obvious why UPA is good for both privacy and scaling. And next I'm going to show you a little bit more about why UPA is also important for interoperability. So first, why UPA? So this is a ZK supply chain at the current stage of blockchain industry. So from the high level, you can think of there is a user, and user will provide some sort of data to the prover, and then the prover will generate the proof, and the proof is getting verified. So this is a very simplistic picture of the ZK supply chain. And of course, the most suitable place to deploy a ZKP verifier is on-chain, because blockchain is kind of like a public, permissionless, censorship-resistant ledger can give you the truth. So, and then there are two kind of ZKP application scheme. The first is a privacy-preserving applications. For example, like private on-chain voting, private token transfer, for example, like a Tornado Cash, or privacy-preserving decentralized identities such as WorldCoin. So in these privacy-preserving applications, the user generated proof on the client side for privacy reasons, and then basically both the user and the prover have to be on the same side or same devices. It could be in your browser, it could be in your phone. And then the user or the client send the proof to the verifier. So the second kind of solution is a scaling solutions, where the user still provide the data, but the prover is run on some beefy machines in Amazon or whatever cloud providers, and then the proof is getting verified on-chain. So you can see in both scenarios, the common interfaces is this like a verifier interface, where the proof is sending on-chain and is getting verified on a blockchain, let's say Ethereum. So that's why we're building UPA. So in our view, we think proofs is going to be the future of all the blockchains. And then it's crucial to scale the proof processing power of all blockchains. We want to upgrade the blockchains from a narrowband ZK to a broadband ZK. To precisely state the problem, you can see verification cost is one of the biggest remaining problems of having more and more proofs. So this is a cost in terms of dollars verify a single proof on chain. For example, today, verify a gross 16 proof costs more than $20, and verify a Hilo 2 KZG proof costs more than $30. And if you want to verify a Stark proof, it will cost you hopping more than $100. So clearly, this is not the future we want to live in. And like Vitalik used to ask this question, do you want to pay $20 to add privacy for your transaction of buying a coffee? And clearly not, right? Because the coffee itself, in most places, is not worth more than $20. So that's why we're building UPA. So what is UPA? So UPA stands for Universal Proof Aggregator. And there are three keywords, right? Universal means these proofs are coming from different circuits. So for example, proof can come from ZK EVM, like Squirrel, Polygon, or could come from coprocessors like Lagrange, where Ishmael just showed you before this talk, or it can come from a privacy-preserving applications such as WorldCoin. We don't care. So NEBRA UPA can aggregate all this proof to a single aggregated proof. And this single aggregated proof is a recursive ZKP proof, basically states that all these previous proofs in these batches, in this current batch, are validated. So now, instead of putting all these different proofs on chain, you just need to prove this single aggregated proof on chain. So all the cost is getting amortized. And essentially, we're building a shared economy of proof processing without hurting decentralization. So if you think about that, basically the more proof, the better economy. Because the more proof you can put a single batch, the better cost you can get. So this is a high-level overview and the properties of the protocol. First, UPA protocol is deployed on-chain, which means the UPA will be deployed on Ethereum, mainnet, and all the major L2s. So this is a permissionless protocol. The sole interface developer or users need to interact with us is a smart contract. So in the sense that, like, you don't need to sign a contract with us. We are permissionless, can aggregate all the proof you want. And second is a censorship resistant, in the sense that we have a forced inclusion mechanism. So in the sense that we cannot censor you even if we want to. Last but not least, it's going to be progressively decentralizable, in the sense that there will be a permissionless way of running the provers, so that you can have even better liveness and censorship resistance guarantee. So next, using NEBRA UPA is extremely simple. So on the left-hand side is how do you verify a proof today on Ethereum and on all the other blockchains. So you have like proof generation or ZKP client, and this ZKP application client could be, for example, rollup as well. You deploy your own verifier contract on chain, and then you send the proof to your own verifier contract. And using NEBRA is almost the same. The only difference here is that you are not using your own verifier contract. You are sending your proof to NEBRA UPA. So we actually tried to give the UPA documentation to many, many users. Most of the users finish their protocol integration within 2 days with very, very minimal code changes. So we launched NEBRA UPA on testnet about 3 months ago on Sepolia. So the high-level overview of the UPA 1.0 here is that it uses a 2+ layers of recursion using Halo 2 KZG. And we actually have built a pipeline and distributed prover serving architecture to harness the power of this like a ZKP. So this is the underlying distributed system work. So UPA has a 2-layer of aggregation circuit. The first layer we call the UBV. Basically, it's a universal batch verification circuit and a pair with a catch-check circuit, which is used to handle public input. And then both the UBA and catch-check proof is aggregated by the aggregation circuit, and this aggregation circuit will produce a final Halo 2 KZG proof and gonna put it on chain. So here, basically, we are leveraging the parallelization here to improve the latency of the recursive proof generation. So the way we do it is that every single circuit you see in this picture is placed in a GPU machine. And so all these GPU machines are working in parallel in a pipeline way to generate proof so that the latency of generating proof is minimized. So in addition to that, we have a pipeline server farm to overlapping the proving over batches. For example, when the first batch comes, our coordinator will spawn the prover cluster 1. While this prover cluster 1 is still working, if at that time the batch 2 comes, the coordinator will spawn a prover cluster 2. So by overlapping the different batches, we can get the maximum throughput as well. So I'll just highlight a few challenges we are building NEBRA UPA. So the first and foremost is ZKP engineering. So one of the challenging places here is that how can we build a non-native arithmetics? So basically, if you're doing recursive proving, you are having this disparity between the data sizes of the proof of your input and the proof you are programming in the circuit. So for example, there is a disparity between the finite field sizes. And this causes like a 20x blow up in terms of circle sizes. And we have like many hard works in terms of we call it like a mathematical hacking. Basically, we leverage all this like advanced mathematics, including like a Chinese remainder theorem, like a Montgomery ladders, all these fancy mathematics to build the most performant non-native arithmetic circuit. And second is how do we handle heterogeneous proofs? So for example, in NEBRA UPA 1.0, we are supporting 3 major versions of gross-16 proofs with arbitrary size of the public input. And in NEBRA UPA 2.0, we will be supporting all the major proof systems incoming. So for us, it's not just about supporting proof systems, it's also about economy. Because the more wider variety of the proof system we are support, the more proof we can aggregate as well. And also, like we are deeply careful about how do architecture system in terms of are we actually using a circuit or we are using a ZK VM. So the short answer here is that circuit is more performant and the VM is more versatile. So in our first generation, we are using a circuit first approach because our observation is that more than 70% of the proof on chain today is just a gross-16 proof, right? So this is the majority of the amount of users we want to support. And we're moving to a VM-based architecture, which means we're actually using both ZK VM and precompiles so that we can achieve best of both worlds in the sense that it's both flexible and performant. So clearly, basically for building the NEBRA UPA, our value proposition here is that because we can make ZKP proof 10 times and more cheaper, this is a huge unlock for the entire ZK industry in the sense that for both privacy and scaling applications, like you will be much, much cheaper to use. So for example, for privacy preserving applications, lower the cost of their ZKP proof from $20 to $2 on Ethereum layer 1, and from $2 to 20 cents on all the major L2s is a huge unlock. So you can acquire your users much more cost efficient. And for the infrastructures, for example, if you are running a ZK-based app chain, you are actually paying about like 15K proof, 15K for proof verification per month, every month, and we can down the cost to 1.5K. So next, I'm going to talk a little bit about the UPA for interoperability. The whole idea here is that we can use proof aggregation to bring native interoperability to ROPs. The idea here is that by using proof aggregation, we can make the cross-ROP transaction the first-class citizen and to be part of a settlement. So for example, right, so this is a high-level architecture of how NEBRA can bring the native interoperability to all the ROPs. So this is a new development we're building. We call it NEBRA OS. So we kind of like a low-key launch that in our own event, Proof Day, about 2 weeks ago. About two days ago. But we will have more information disclosed incoming. So the whole idea here is that first, you can make cross-ROP transactions. Basically, you can think of as the transaction bundles as a first-class citizen. And then users don't send these transaction bundles directly to the ROP. You can send to the coordination module. And the coordination module will basically ask all the ROP sequencers to say, hey, are you going to promise to include these cross-ROP transactions in the next epoch? If everyone said yes, so there is a safety module to generate the inclusion proofs for these transactions. So basically, during the settlement of this ROP state root, the proof aggregation module is going to aggregate both the validity proof from all the different rollups together with this like a meta transaction inclusion proof. So basically, this proof aggregation module can hold all this rollup as a hostage, so that making sure if they committed to include these cross rollup transactions in the next epoch, they have to. Otherwise, their state root is not getting settled. And in the future, we can put more fancy type of intent safety proofs as part of a proof aggregation. So for example, let's say if you not just want to do a cross rollup swap of your asset, you want to having a price guarantee. So for example, you want to swap this Arbitrum OP token with like this ARB token at a certain price guarantees. So we can do that natively in the settlement layer so that you can have safety guarantees without relying, for example, all this like cross-chain liquidity providers. And so this is a high-level picture of how does proof aggregation can enable interoperability. So here is my claim. I do think native interoperability is an ecosystem-wide analog. So here, this is a list of the advantages we can have if you have native interoperability. First, it will fix the security leakage of cross-rollup transactions. So it's actually well known today, despite from the L1 to L2 transactions on rollup is secure, all the cross-rollup transactions, because we don't have proof aggregation, it still requires unsafe cross-chain bridges with liquidity providers. And here, most of the times, the liquidity providers are taking the risk of the settlement. So for example, despite optimistic rollup takes 7 days for settlement, right? So as a normal user, you can do your cross-chain transaction very quickly because all this risk is taken by all these liquidity providers. But in some sense, there's no free lunch here. Because these liquidity providers taking the risk, right? All this risk is priced in with your cross rollup transaction cost. So now, basically, we're saying if you have native interoperability, these security costs will be much, much cheaper for your cross rollup transactions. And second, like I said before, you could have enforceable cross rollup intent, which means for all these cross rollup transactions, you can have native interoperability and also you can have intent safety guarantee, which means you can have user express their preferences of how this transaction getting done, and we as a proof aggregation settlement layer can enforce that. Next is that it will actually provide better developer experiences for both chain abstraction and wallet builders. And like I said before, it will actually provide better capital efficiency for cross-rollup market makers. And also as a result, right, so today, if you are building a new app chain, you have a huge amount of burden of bootstrap liquidities. And now, because you can frictionlessly tapping the cross-chain liquidity by having native interoperability, it will actually give you less liquidity requirement to start a new chain. And next, we do think it can enable new use cases. For example, like a pure asset chains or like a pure DEX chains, like a uni chain, to fix up abstraction leakage. So in general, right, so we think native interoperability means lower user friction and better UX in general. So I would like to conclude my talk here. So to conclude, right, basically I show you what we're building in NEBRA UPA and how can we use NEBRA UPA to bring, to lower the cost and then to enable better privacy, scalability, and native interoperability. And so we are building this NEBRA OS, this native interoperability for all the Ethereum-based ZK rollups. If you want to get a white paper, scan my Telegram. I'm happy to give you the preview of the white paper before we publish that. And with that, thanks a lot. That's the end of my talk. Yeah, thank you.